Exponential and logistic functions are discussing when we have our variable in the exponent. So with an exponential function, like I said, the variable is in the exponent spot. With that being said, a cannot equal 0, because if it does, then you don't have a function whatsoever. And b cannot equal 1. Okay, because otherwise you're getting a repeat of 1 to the power of whatever, and that's always going to be 1. So that's why our b can't be that. The a value is our initial value. And the initial value is basically where are you starting. The b value is our base. This is sometimes called the decay or growth factor. Okay, and x is our variable that we're plugging into. So with that, if you have anything in the form of your exponent with a number, that does not represent an exponential function because that variable or that x has to be in that exponent spot. So that's good information to have there. So for instance, just as a quick refresher here, if I were to have the equation y equals 3 times 4 to the power of x, in this case, my initial value is the 3, and my base is that 4. The x is in the exponent spot, so we're good to go that this is an exponential function. Looking at our transformations of different functions, we've been doing this now with several different types of functions, whether it was a linear function, quadratic function, etc. Talking about what happens when this changes our function. So if I were to have f of x equals, let's say that my parent function is 2 to the power of x. So what happens if that function, the x is changed to plus 3? So what happens here is we're going to be looking at, since it's with the x variable, we know that we are going to have a horizontal shift, left or right, because it's attached with that x. So because it is with the x, remember it's always opposite of what we see. So this plus 3 represents a shift to the left 3. If you were to have a number in front of that x variable, so say it was to the power of 2x, that is going to give us a stretch because we're multiplying. Okay, so this is all information, we just keep building off of it. If you were to have, let's say, a different function, let's still go with that, but let's say we have a negative x. So because that negative is attached there, we know that we have a reflection, and that's going to be over the y-axis. So we're just looking at those different transformations that we've talked about of what happens if this occurs. Whether we have a horizontal shift, a vertical shift, do we have a reflection, do we have a stretch, whether it's a vertical stretch or a horizontal stretch. So just looking at those different types of things. The next thing, we talked about exponentials. I will show you in class, if you're given a data set, how to find that exponential equation. But the last one we need to talk about is logistic. With a logistic, we are in the form of f of x equals c divided by 1 plus a times b to the power of x. Sometimes this is represented with a little bit different if we have the e, where we have a number, I know it doesn't look like an E doesn't seem like a number, but remember, it's kind of like pi. It is a number. It's 2.718 to be exact. So you will see a logistic in both ways. Majority of the time you'll see it in the latter way just because we're dealing with a decay situation, and that's not that big of a deal. It's just there. With that logistic, the A and the B are still representing the same thing. The C, however, is representing a limit to the growth. So we use logistic equations when we're talking about having a cap or a maximum or a minimum on that growth or decay. So for instance, if I'm looking at my classroom, I have a cap on the number of seats I have in my classroom. So that C value would happen to be in my classroom right now would be 23. I have 23 student desks, so that C value cannot go over that. So that's just different things looking at that. With this specifically, we'll work more with this later on when we're dealing with populations, growth, or decay, that kind of stuff. I'll talk about a little bit about that in class, but mainly the thing is, looking at this, can you see what the information is talking about? So for instance, let's say that I have the function f of x equals 20 divided by, let's go with 1 plus 2 times 0.5 to the power of x. So looking at this information, can I determine the initial starting value? Can I determine what is my base? Can I determine what's the limit? Okay, so the A value here is 2, the B value is 0.5, the C value is 20. Do you know that information? Can you graph this information and find, you know, your intercepts? Can you find your asymptote lines? Can you do all of that stuff? So even though it's a new situation, we're just scratching the surface. We'll go a little bit deeper with this later on. So that is, for right now, exponential and logistic functions. We'll talk more about that modeling in the next section.